Hi everyone, and welcome to this talk on unpacking Java containers. I'm excited to share with you today some things that I've learned about containers, which of course are still all the rage right now. And I hope that you come away today with a better understanding of the history behind containers and how they actually work on your system and some of what is going on under the covers. I think this is important for a developer to know, especially just to get your head wrapped around what's going on and how your application is going to behave on production systems. The slides and additional information about this talk will be available on jfrog.com/shownotes, which I've linked here. So just a little bit about me. My name is Melissa McKay. I started with JFrog as a developer advocate in February. That's good, going on 6 months now. I've come from a developer background, and I've been a developer for over 20 years now. Most of my experience has been in server-side development in Java, but I've had the privilege of working on many different teams over the years in a variety of different technologies, languages, and different tool sets. I've been on large, small teams, big, small companies, and like most of you, I've had my share of frustrations and successes. Along the way, I discovered a passion for diving in deep to understand things, sharing what I've learned, and hopefully improving processes along the way. I started speaking a few years ago. I decided that was something I wanted to do more of, so I threw my hat into the ring to become a DA with JFrog, and now I'm here today, privileged to speak with you about virtual containers. So let's get started quickly. We'll begin with a brief history to give some background context. Hopefully this won't be too boring, but there are some important milestones in the past that are important to know. We'll take a look at the container market and what's been going on the last few years. Then we'll move into getting a real understanding of what Docker is. Docker is not synonymous with containers. After that, we'll be in an excellent place to talk about what a container actually is. Then we'll review a common container gotchas. And finally, I'll leave you with an option for managing your images. And without further ado, let's jump in and start learning. So now I know some of you are wondering if you're in the right place, because that's not the typical shipping container photo that you were expecting. But there's a couple reasons I chose to show bananas here. First and foremost, I'm tired of seeing shipping container pictures and graphics on every presentation about Docker or containerization in general. So I've started a rebellion. I'm just not going to do it. Second, this is really a story about how our industry has adapted to dealing with limited resources over time. Bananas isn't really random. It actually reminds me of a story that my grandfather would tell me when I was growing up, and that went like this. When my grandfather was a kid, he would get a banana once a year on Christmas. This must have been during the 20s and the early 30s. Bananas were such a treat during that time that none of that banana would go to waste. He and his siblings would take a fork and scrape the banana peel to get every last bit of banana off, because there likely wouldn't be another one until next Christmas. Now, maybe it isn't the best analogy, but I liken that story to how computing resources were in the 1960s and 70s. Very limited and very expensive. On top of that, it took forever to get anything done. Often a computer would be dedicated for a long period of time to a single task for a single user. Obviously, the limits on time and resources created bottlenecks and inefficiency. Just being able to share was not enough. There needed to be a method to share without getting in each other's way or having one person inadvertently causing an entire system to crash for everyone. Necessity is the mother of invention. So the need for better strategies in sharing compute resources actually started a path of innovation that we see massive benefits from today. There are some key points in time that brought us to the state we are in today with containers, and we'll go over these. I'm going to begin our container history lesson with Chroot. Chroot was born in 1979 during the development of the 7th edition of Unix and was added to BSD in 1982. Being able to change the apparent root directory for a process and its children results in a bit of isolation in order to provide an environment for testing a different distribution, for example. Chroot was a great idea and solved some specific problems, but more was needed. The jail command was introduced by FreeBSD in 2000. Jail is a little more sophisticated than chroot in that it includes additional features to help with further isolation of a system. It isolates file systems, users, and networks, and gives the ability to assign an IP address to each jail. In 2004, Solaris Zones brought us ahead even further by giving an application full user, process, and file system space and access to system hardware. Solaris Zones also introduced the idea of being able to snapshot a file system. This will become important later. In 2006, Google jumped in with their process containers. These were later renamed cgroups, which centered around isolating and limiting the resource usage of a process. Moving right along, in 2008, cgroups were merged into the Linux kernel, which along with Linux namespaces led to IBM's development of Linux containers. 2013 was a big year. Docker came on the scene, bringing their ability to package containers and move them from one environment to another. The same year, Google open sourced their Let Me Container That For You project, which provided applications the ability to create and manage their own subcontainers. From here, we saw the use of containers, and Docker specifically, absolutely explode. In 2014, Docker chose to swap out their use of the LXC toolset for launching containers with libcontainer in order to utilize a native Golang solution. I'm almost done with my history lesson here because from here on, you would just start seeing a ton of names of projects, organizations, specs, etc., that are just a little confusing if you have a better, until you have a better understanding of how containers work. Another event I want to bring up, however, June 2015. This is important to know about because it will give you some insight into some of the activity and motivations behind shifts in the market. The Open Container Initiative was established. This is an organization under Linux Foundation that includes members from many major stakeholders, including Docker, with the goal of creating open standards for container runtimes and image specification. So while all of this is happening in the container world, there's a couple of other dates that are going to be important to Java devs specifically. Java 7 was introduced and released in 2011. Right after work on 2008 was started, 2008 was released in 2014, actually in March of 2014. This is going to be important, and I'll bring this up again later. When you start containerizing your Java applications, this little bit of history will be important to know. Anyway, that's it for our history lesson right now. So let's take a look at what's been going on in the market recently concerning container runtimes. I did a little hunting and found that for the last 3 years, Sysdig, a company that provides a really powerful monitoring and troubleshooting tool for Linux, many of you might already be aware, has put out a container report based on analysis of their users. Part of the report includes data on container runtimes that are in use. In 2017, they analyzed data from 45,000 containers. And there's no graph available for this because 99% of the containers were Docker, so they didn't split up the results. In 2018, however, we start to see a little bit of a change. They analyzed data from over 90,000 containers, which is double their sample size. 83% of these were Docker, 12% CoreOS Rocket containers, 4% Mesos Containerizer, and 1% LXC. So it looks like at this point, other container runtimes are starting to encroach a little bit on the Docker space. Moving on to 2019, the latest Sysdig container report included stats from over 2 million containers. Docker is still holding relatively strong at 79%. 18% is Containerd, but it's worth noting that Containerd is a runtime that Docker actually builds on top of. The last 4% is Cryo. I don't know that there is enough data here to determine whether Docker will stay on top in the future or if something completely different will prevail. That remains to be seen. But this data is interesting, especially because of what's been happening over the last few years. So now that I've introduced a few of these other container runtimes that exist out there besides Docker, it's time to start talking about what a container actually is and what Docker actually provides in order to appreciate the differences between them. So what exactly is Docker anyway? This is key. What Docker had over the other players in the container game was a focus on commoditizing a complete solution that made it easy for developers to package and deploy their applications. Once containers became easy to use, we all witnessed the explosion of tools and resources around them, and the Docker image format rose to become a de facto standard in the market. The stats I just showed from Sysdig are specific to container runtimes. That terminology is important to understand here. I'll explain the pieces and parts involved in working with containers, and you'll immediately understand why Docker sucked up the market so quickly. So as users, let's think about what we actually need to get our apps out there and running. Every innovation that is coming out of this space is purely based on what users need and want, whatever the motivation is behind it. If a user needs or wants something bad enough, there's a huge opportunity there for solution providers. That seems like a common sense thing to say, but so often we can find ourselves getting so far down into nitty-gritty details that we lose sight of the actual problem we are trying to solve. This leads to a ton of missed and overlooked opportunities. So here's a list of needs broken up into discrete features. First and foremost, we need the container itself. Some of you might be asking about virtual machines at this point, and discussing VMs is out of the scope of this session, so I'm not going to go into deep. I'm not going to go deep into the differences between them or why you would choose one over the other. But the one thing I will say is that a virtual machine is not synonymous with a container. A container feels like a virtual machine, but the biggest difference is that a VM includes an entire OS all to itself, and containers share the system's OS. The point of the container is to be lightweight and have the ability to move from one environment to another seamlessly and quickly. That said, I know there are developments happening in the VM space, but that's a topic for another time. So the rest of this list. We need an image format to define a container. We need a way to build an image of a container, a way to manage images, a way to distribute and share images, a way to create, launch, and run a container environment, and a way to manage the lifecycle of the running containers. I didn't even get into orchestration like Kubernetes or anything like that, but this is plenty to prove my point. So Docker was ready with an answer for everything. You want to start using containers? Well, you can use Docker Engine. You need an image format? Well, here's the Docker image format. You need a way to build an image? Use a Docker file and call Docker build. You want to manage images? There's a couple simple commands here. You can call Docker images. You can call Docker remove. You want to share your images or use an image from someone else? Call Docker push or Docker pull. Oh, and there's Docker Hub, where you can store and share your images. You need a way to launch, run, and manage your containers and their lifecycle? Call Docker run, Docker stop, Docker PS. Docker succeeded in quickly meeting the immediate needs of the container-hungry market. On top of that, the tool sets Docker provided made it all easy. It was enough to walk away with a tremendous part of the market share, all the way down the aisle. So remember in our history lesson when I spoke about the Open Container Initiative, out of all of those features that we just went through that Docker offers, there are two that were taken up for the cause by the OCI, the image format and the container runtime. Docker did quite a bit of reorganizing their code base, developing abstractions and pulling out discrete functionality. They are a heavy contributor to the OCI, giving the Docker v2 image spec as a basis for the OCI image spec, and RunC, which was contributed as a reference implementation of the OCI runtime spec. There are quite a few other container runtimes out there making waves now, including Containerd, cryo, and kata, all with various levels of features for specific use cases. It's worth pointing out that Containerd was actually contributed by Docker to the Cloud Native Computing Foundation and internally uses runc. Containerd has also been integrated into Docker and has been in use since version 1.11. That came out in 2016, so it's been out there a while now. The next few years will be interesting to observe what happens with these specs and how the OCI moves forward. There's quite a range of differing opinions about what should and should not be in the standard for a container runtime. And we're in a situation right now where using a runtime that just meets the requirements of the OCI spec doesn't seem to be enough. I've added a couple of links here that are excellent starting places to learn more about container runtimes if you're curious. The second one specifically is the beginning of a blog series by Ian Lewis, a Google dev advocate. The first subtitle in that blog is literally, "Why are container runtimes so confusing?" Which, when I read that, I agreed with right away. Why? Why are they so confusing? Anyway, Ian does a really good job of succinctly explaining some of this. Now that we understand all that Docker entails and some of what's going on in the market, let's focus just on the container itself and what that actually looks like on your system. I'll show you how it's stored and what is actually happening under the covers. You'll discover pretty quickly that images and containers aren't really all that magical. My first experience with containers was as a new developer on a project with a tight deadline, of course. I could argue that's a good description of most projects. The best course of action for me was to just jump in and start getting something up and running on my local machine. I learn best by doing, and the Docker documentation is actually really good. So if you find yourself in a similar position, I recommend going through their Get Started docs, which I've linked to here. Going through this guide will get you somewhat comfortable with some of the Docker commands that you're going to need. The first thing to note is that a Docker image is really just a tarball of a complete file system. When an image is unpacked, it's just thrown into its own directory, which becomes its root file system. The second is that the processes that are involved in running the containers are just regular Linux processes. On top of that, there are just a few Linux features that are used together in a way to achieve the isolation that we want from containers. Namespaces are an important ingredient. This is what is used to provide virtual separation between containers, and this is how the processes inside a container don't interfere with the host or processes inside another container. Here you can see the namespaces that were set up for a Postgres container that I have on my box. The cgroups functionality is integral to constraining how much a container can use things like CPU, memory, network bandwidth, etc. I can set these constraints by including options on the Docker run command when launching an image. And here you can see that I've constrained the image usage, the memory usage limit on one of my containers here. I want to quickly gloss over some file system details, where containers and images are actually stored on your file system. First off, after you've installed Docker, running the command docker info will spit out a bunch of information about your installation, including the Docker root directory. This is where most everything you're going to care about regarding your Docker images and containers will be stored. Note that if you're on a Mac, your containers are actually running in a tiny VM. So you're going to need to use screen or something to get in there and get to the Docker root directory to look around. And if you're not familiar with how to use the screen command, definitely look that up, Google that to get familiar with it first. It will mess up your text display pretty good if you don't enter and exit screen the right way. This slide shows how you can get information about the images that you have stored on your system. First, I listed my available images using the Docker images command. I actually have several installed right now, but I'm only going to show the first couple in the list. Using the Docker inspect command, I can inspect any image I like using its image ID. This will spit out a ton of interesting information. But what I want to highlight here is the graph driver section, which contains the paths to the directories where all of the layers that belong to this image live. Docker images are composed of layers, which represent instructions in the Docker file that was used to build the image originally. These layers actually translate into directories, and these layers can be shared across images in order to save space. The lower dir, merge dir, and upper dir sections are also important. The lower dir directory contains all of the directories or layers that were used to build the original image. These are read-only. The upper dir directory contains all of the content that has been modified while the container is running. If modifications are needed for a read-only layer in lower dir, then that layer is copied into the upper dir, where it can be written to. This is called a copy on write operation. It's important to remember that the data in the upper dir is ephemeral data, and that only lives as long as the container lives. In fact, if you have data that you intend to keep, you should utilize the volume features of Docker and mount a location that will stick around even after the container dies. This is how most containers running a database are run, for example. Lastly, the merge dir is kind of like a virtual directory that combines everything from lower dir and upper dir. The way the union file system works is that any edited layers that were copied into upper dir will overlay layers in the lower dir. This slide shows that I have actually a few containers running on my system. 2 of them are my local JFrog Container Registry installation, which includes a container for ARTIFACTORY and a container for a Postgres database. The other is a simple test container I was playing around with. Note that the container IDs of the running containers match up with the container subdirectory names. Something to remember here is if I stop a container, that corresponding directory doesn't automatically go away until the container is actually removed with the docker remove command. So if you have stopped containers lying around that never get cleaned up, you might see your available space start to dwindle. There is a docker prune command that you can run every now and then that will help keep things cleaned up. Or you can launch your container initially with a flag that indicates it should be removed when it's finished running. A lot of orchestration will also take care of this for you as well, but this is important to know just running an individual container. So the tool sets around building and running images and containers have made things so easy that it's easy to shoot yourself in the foot in a few places. Here are 3 of the most common gotchas, plus 1 JVM specific gotcha that I ran into almost immediately when I first started working with containers. The first is running a containerized application as the root user. I'll be honest here, when I was initially getting containers up and running, I was so excited about how well they were working that it was a while before I took this one seriously. But now that you know that processes inside a running container are just like any other process on the system, albeit a few constraints, it's scary now to run as root inside a container. Doing that opens up the possibility of a process escaping the intended confines of the container and gaining access to host resources. The best thing to do is to create a user and use the user command inside the Docker file when the container is built in order to run processes as that user. There is a way to specify a user when the Docker run command, when using the Docker run command, but that leaves open the possibility of forgetting to do that. So it's nice if the image is set up by default not to run as the root user, and that way you won't risk problems when someone unexpected has escalated and has privileges they shouldn't have. Also, pay attention to official images that you pull from Docker Hub, whether or not they run as root or if they leave that part up to you to figure out. Make sure you know what's going on inside of your base images. So the next one, even though Docker provides you with the ability to set resource limits on your container, it doesn't automatically do it for you. In fact, the default settings are a free-for-all with no limits anywhere. Make sure that you understand the resource needs of your application. Too little and your container will die from starvation. Too much and the container could smother others on the system. The resource usage of your containers is something that you're going to want to monitor over time and adjust as needed. It's a very good way also to determine if something is going wrong or if load on your system has changed for some reason. So never updating. This is a pretty big security issue, and this happens all the time. It's easy to get complacent and not pay attention to what is actually getting pulled in when you build images. Not only do you need to be aware of outdated versions that you specify in your own Docker file, but you need to pay attention to what's in the base image it's coming from. Not updating packages and libraries inside your container can lead to some pretty embarrassing results, especially when there are tools available now to alert you when the security issues have been discovered with specific artifacts. So this leads me right into Java JVM specific, gotcha. And this is also about versioning. This is also related to being very much aware of what your application requires to run successfully regarding memory. Remember early in our history lesson when I mentioned the dates for Java 7 and Java 8 releases? Well, the JVM is pretty clever at automatically determining settings for your swap and heap and your garbage collection behavior based on things like the memory and the number of cores available to your application. But considering the timeline of when Docker came out and when these Java versions were released, 7 and 8, and certainly earlier versions, are not fully container aware. This means that your Java application won't necessarily obey any memory and CPU constraints that you have put on your container, and you may end up with some surprise out-of-memory killer activity. The reason for this is that the mechanisms the JVM uses to retrieve the resources available come from the actual host machine and not the cgroup limits that you would expect. There were some improvements around container awareness introduced in Java 8, update 131 to be specific, and further improvements in later versions. But if at all possible, you really should get to Java 11, the latest available LTS release that is container aware. If you're stuck on a legacy version, however, which I know many people are, all is not lost. You just won't be able to depend on the JVM automatically determining the best use of resources for you. Instead, you'll need to explicitly set the necessary flags for memory and the number of garbage collection threads based on the limitations that you want to set on your container. So, tools that can help manage your images. JFrog Artifactory supports Docker registries and images. You can use it just like you do for other types of artifacts, both as a cache for third-party base images and as your own internal registry. After uploading your Docker images, you have the ability to gather statistics and even drill down into each layer of an image for more information. If you've integrated a CI/CD solution, you can also determine what build produced a particular image or what builds used it. Another thing that is advantageous for your CI/CD solution, especially in an application like Artifactory, having all of your binaries in the same place is really valuable. You can follow through and tell exactly where your Java binaries came from, how your image was built, what builds they were all combined and packaged together with. All of that information is extremely valuable. So we discussed earlier the problems with not updating images regularly. JFrog X-Ray is a security scanning tool that will alert you if there are known security vulnerabilities or even licensing issues with your artifacts. For Docker images, it's especially useful because it has the ability to drill down into the layers of the image to find exactly which library or package has been flagged as a problem. You have control over how sensitive these alerts are and what actions to take when they're triggered, whether to fail a build, prevent a download, or simply send a notification about the problem. All right, we've come to the end of our time here. Thank you everyone for coming. I hope that you enjoyed this session and that you got something to take out of it to take back to your teams, or just that you learned some detail that you didn't know before. Feel free to reach out to me with any questions you have, and enjoy the rest of the conference.